G'day viewers. In this episode we're going to add another dimension to the scaling problem discussed in previous episodes. We shall look at certain aspects of the physical modelling involved in the Project Gravitaur documentary. It is essential to understand that the key physical artefact associated with the sports model spacecraft was the element 115 primary wedge. Moreover, the key operating principle associated with the primary wedge is the gravity A wave fundamental wavelength. In addition to this, the key design principle associated with the primary wedge is 1/4 of the gravity A wave fundamental wavelength. In other words, the sports model spacecraft is literally designed around the element 115 primary wedge, and consequently the spacecraft is basically one large antenna. This means that if the dimensions of the primary wedge are inaccurate, then the entire visual representation of the sports model spacecraft may also be inaccurate. In formulating their documentary, Project Gravitaur leadership consulted with Lazar in order to build 3D computer models and simulations of his experience at S4. As you would expect, these 3D simulations contain dimensional information which has been endorsed by Bob Lazar. Fortunately, Project Gravitaur leadership shared certain critical dimensional information with us. From this, we were able to establish that the mass density of the element 115 primary wedge does not equal the Bob Lazar endorsed value of 31.5 grams per centimetre cubed. In other words, the element 115 primary wedge dimensions in the Project Gravitaur documentary are inaccurate. Consequently, we were able to quantify the embedded error at the centre of the sports model spacecraft design. Viewers need to keep in mind that the key operating principle for the sports model spacecraft is centred around the gravity A wave emanating from the element 115 primary wedge. As mentioned previously, the sports model spacecraft is basically a very large antenna. Hence, if the dimensions of the primary wedge are inaccurate, then the entire visual representation of the spacecraft may also be inaccurate. Having said this, the Project Gravitaur team have implemented every practical means to ensure that the documentary conveys Bob Lazar's experience at S4 as accurately as possible. Of course, it should be expected that the information provided by Bob Lazar from memory, which dates back to 1989, will carry a certain amount of dimensional error after so many years. Please remember that Bob Lazar is human. He ages like the rest of us, and he loses memories like the rest of us. Thus, we estimate that viewers should allow a margin of error of somewhere between 1 to 10% regarding the sizes of all the objects appearing in the Project Gravitaur documentary. Possibly the most interesting characteristic of the 3D computer models and simulations included in the Project Gravitaur documentary is that Bob Lazar's primary wedge dimensions align astonishingly well with an element 115 mass density value of 13.5 grams per centimetre cubed, not the mass density value of 31.5 grams per centimetre cubed endorsed by Bob Lazar. In other words, the physical dimensions of the sports model spacecraft reproduced in the Project Gravitaur documentary seem to favour the standard scientific value of element 115 mass density, not the value endorsed by Bob Lazar. This is a significant mathematically verifiable fact which should not be trivially dismissed. In other words, we have discovered at least one potential contradiction. So, what does this mean? Well, it means that the core scientific mystery in the Bob Lazar experience at S4 is the reconciliation between the standard scientific value of element 115 mass density and the claimed value of element 115 mass density. In other words, reconciling the difference between what we have termed the Frick and Lazar limits. It is also important to note that the same core issue featured in our scaling problem episodes. Okay, let's begin our adventure by considering some ideal configurations. We saw in episodes 108 and 109 that we may represent ideal configurations in accordance with episodes 52 and 65. The key design principle is that the engineering solution is anchored to 1/4 R, that is, 1/4 of the gravity A wave fundamental wavelength. Thus, viewers should notice that the primary wedge thickness equals the disk thickness, which also equals 1/4 R, and in turn also equals 1/4 of the gravity A wave fundamental wavelength. As you can see on screen, we have provided solutions pertaining to different isotopes of element 115. Moreover, we have emphasised the cylinder heights in the Potter and Storti limits as being greater than or equal to 3R. This boundary condition relates to the minimum 12-disc primary wedge manufacturing solution asserted by Emeritus Professor Paul Edwin Potter in his book titled Gravitational Manipulation of Domed Craft. Okay, let's now look at operational configurations. We're going to look at two operational limits, the Storti limit and what we shall call the Lazar limit. The Storti limit has already been defined, so we only need to define the Lazar limit. To do this, we shall reverse engineer Bob Lazar's endorsed element 115 mass density of 31.5 grams per centimetre cubed. You can find the link to the reverse engineering solution algorithm at the bottom of the slide. However, I should accentuate that the reverse engineering solution algorithm insists upon the stable existence of element 115 with 562 neutrons, yielding isotope 677. In previous episodes, we have declared that element 115 may not have been utilised by Bob Lazar. Rather, possibly another element was utilised instead, perhaps element 247. Nevertheless, for the purposes of the solution algorithm herein, we shall assume that isotope 677 exists and is stable, despite the fact that the neutron-to-proton ratio is almost 5, that is, seemingly impossible. Once again, we have emphasised the cylinder heights in the Storti and Lazar limits as being greater than or equal to 3R. This boundary condition relates to the minimum 12-disc primary wedge manufacturing solution asserted by Emeritus Professor Paul Edwin Potter in his book titled Gravitational Manipulation of Domed Craft. Thus, in establishing our operational configurations, we have incorporated the contributions from as many credible sources as possible. It should also be noted that the Storti and Lazar limits appearing on screen do not incorporate the effects of nuclear binding energy within the element 115 nucleus. However, even if we include nuclear binding energy as high as 1% of nuclear mass in our calculations, it does not significantly alter the limits shown. Please refer to the link appearing at the bottom of the slide. Okay, so far we have defined the ideal and operational configurations. Let's now look at what Bob Lazar has to say. According to information gathered by Project Gravitaur, Bob Lazar claims to have utilised a 10-disc primary wedge solution at S4. However, he recognises the possibility that it may have been a 12-disc solution instead. Bob obtained this information in 1989, so it is entirely plausible that he may have forgotten some important details by now. On the right-hand side of the slide, we show the ideal electrogravimagnetic 16-disc configuration with 10-disc, 12-disc and 13-disc solutions overlaid. As labelled, you can see that the 10-disc solution is attributable to Bob Lazar, whilst the 12 and 13-disc solutions are attributable to Emeritus Professor Paul Edwin Potter. The 12-disc solution denotes the minimum recommended configuration, as asserted by Potter in his book titled Gravitational Manipulation of Domed Craft. Seemingly for good measure, Potter added an additional disc in his depictions of the primary wedge manufacturing process in order to convincingly satisfy his minimum 12-disc requirement. However, what Potter did not know was the physics behind the so-called minimum disc requirement. In order to ensure that a gravity A-wave signal of sufficient magnitude is accessible so that it may be amplified, the height of the primary wedge must end with a full wave or a half wave, that is, a node. This means that disc configurations resulting in 1/4 wavelengths should be avoided. In practical terms, stacks of 10, 12, 14 or 16 discs are favourable, while stacks of 11, 13 or 15 discs are unfavourable. In other words, without Potter realising it, he specified an unfavourable 13-disc configuration in his book. As of the production date of this video, the Project Gravitaur website displays this image of Bob Lazar holding a primary wedge with a model of the element 115 reactor in the foreground. Given that Project Gravitaur's objective is to accurately reproduce Bob Lazar's story in a visual sense, we may assume that Bob Lazar has endorsed the dimensions of the primary wedge appearing in the image. Hence, this image begs the question, what are the dimensions of the primary wedge?
Fortunately, precise dimensions have been supplied to us by Project Gravitaur leadership, but unfortunately we are unable to share those dimensions with you due to a confidentiality agreement. However, what we can share with you is the information appearing on the left-hand side of the slide. We can confirm that the element 115 primary wedge appearing in the Project Gravitaur documentary does not constitute material with a mass density of 31.5 grams per centimetre cubed. Similarly, it does not constitute a mass of 223 grams. It is approximately 30 grams less than the required value. This means that sufficient error exists in all three physical dimensions approved by Bob Lazar that the scale of the mock-up appearing in the Project Gravitaur documentary is a useful approximation only, not an exact reproduction of what Bob Lazar utilised at S4. This of course brings into question other artefacts appearing in the documentary. Having said this, we shall work around the scaling issue by constraining the base length and the height to base length ratio of the primary wedge to the dimensions derived via the electrogravimagnetic construct. When we do this, we astonishingly find an almost perfect fit. In other words, we find that the remaining unconstrained dimension of primary wedge thickness is approximately 94% similar to the value endorsed by Bob Lazar via Project Gravitaur leadership. As a bottom line conceptual summary of what we do with respect to the primary wedge is that we constrain, that is anchor, everything except the primary wedge thickness to 1/4 gravity A wave fundamental wavelength. Viewers should not lose sight of the fact that the alien spacecraft Bob Lazar worked on at S4 was entirely built around the gravity A wave fundamental wavelength and by association the element 115 primary wedge. In essence, the alien spacecraft is one very large antenna, and everything is designed and fabricated with this in mind. Okay, let's now run the numbers through our spreadsheet calculator. In these two scenarios, we are working with full-scale models, both of which utilise the value of mass density for element 115 endorsed by Bob Lazar, that is, approximately 31.5 grams per centimetre cubed. Unfortunately, in scenario 13, we were forced to redact information indirectly provided to us by Bob Lazar via Project Gravitaur leadership, due to a governing confidentiality agreement. As we stated on the previous slide, the element 115 primary wedge appearing in the Project Gravitaur documentary does not constitute material with a mass density of 31.5 grams per centimetre cubed. Similarly, it does not constitute a mass of 223 grams. It is approximately 30 grams less than the required value. In fact, the mass density of element 115 required to yield a primary wedge mass of 223 grams, according to the Project Gravitaur documentary, is 36.34 grams per centimetre cubed. The value of disk thickness appearing in scenario 10 agrees to 94% similarity with the Bob Lazar endorsed value revealed to us by Project Gravitaur leadership. Please remember that the value of disk thickness shown is based upon a triangular prism approximation of the primary wedge, not its geometrically exact volume. The important takeaway from scenario 10 is that the electrogravimagnetic construct saves the day by compensating for the primary wedge dimensional errors embedded within the Project Gravitaur documentary. Okay, let's now summarise what we have learned. Our analysis yields 7 key artefacts. The first artefact is the Potter limit. The Potter limit is a set of boundary conditions defined by Emeritus Professor Paul Edmund Potter based upon his investigation and interpretation of Bob Lazar's claims. The boundary conditions defined by Potter include the minimum number of element 115 disks required to fabricate a primary wedge. Hence, by association, this includes the minimum required element 115 cylinder height. In addition, Potter's boundary conditions also include the diameter of the waveguide assembly, as well as the internal diameter of the element 115 antimatter reactor dome. The second artefact is termed the Frick limit. The Frick limit denotes the electrogravimagnetic construct solution which aligns with element 115 isotope 290 possessing the Burckhardt-Frick mass density estimate of 13.5 grams per centimetre cubed. Similarly, the third artifact denotes the electrogravimagnetic construct solution, which aligns with the element 115 isotope 296 possessing the Staughty mass density estimate of 13.8 grams per centimetre cubed. The fourth artifact is termed the Lazar limit. This has been derived utilising the element 115 mass density value of 31.5 grams per centimetre cubed, which has been endorsed by Bob Lazar. We reverse engineer Lazar's mass density value via the electrogravimagnetic construct in order to establish the boundary conditions shown. The fifth artifact involves the technical assertions embedded within the Project Gravitaur documentary. The importance of this artifact is that it quantifies the embedded error at the centre of the sports model spacecraft design. Viewers need to keep in mind that the design principles for the sports model spacecraft are centred around the gravity A wave emanating from the element 115 primary wedge. The sports model spacecraft is basically a very large antenna. This means that if the dimensions of the primary wedge are inaccurate, then the entire visual representation of the spacecraft may also be inaccurate. Having said this, we want to emphasise that the Project Gravitaur team have implemented every practical means to ensure that the documentary conveys Bob Lazar's experience at S4 as accurately as possible. Of course, it should be expected that the information provided by Bob Lazar from memory, which dates back to 1989, will carry a certain amount of dimensional error after so many years. Please remember that Bob Lazar is human. He ages like the rest of us, and he loses memories like the rest of us. Thus, we estimate that viewers should allow a margin of error of somewhere between 1 to 10% regarding the sizes of all the objects appearing in the Project Gravitaur documentary. The sixth artifact lists 4 significant disk stack solutions. The primary wedge appearing in the Project Gravitaur documentary is fabricated from the 10-disk solution. However, Bob Lazar asserts that his recollection could be challenged in favour of a 12-disk solution. A 12-disk solution is consistent with the claims made by Emeritus Professor Paul Edwin Potter. As you can see, we have emphasised the 12-disk solution in each limit configuration by the rounded purple box. In order to ensure that a gravity A wave signal of sufficient magnitude is accessible so that it may be amplified, the height of the primary wedge must end with a full wavelength or a half wavelength, that is, a node. This means that disk configurations resulting in 1/4 wavelengths should be avoided. In practical terms, stacks of 10, 12, 14 or 16 disks are favourable, whilst stacks of 11, 13 or 15 disks are unfavourable. The seventh artifact lists the astonishing similarity between the predictions generated via the electrogravimagnetic construct and the technical information affirmed by Bob Lazar in the Project Gravitaur documentary. Please consider that the Potter, Frick and Staughty limits were predicted between February 2023 and October 2023, that is, long before our contact with Project Gravitaur leadership. However, the Lazar limit is something we prepared for this episode. Possibly the most interesting feature of these 7 artifacts is that the Frick limit, which aligns with Bob Lazar's technical specifications astonishingly well, is based upon an element 115 mass density of 13.5 grams per centimetre cubed, not the mass density associated with the Lazar limit of 31.5 grams per centimetre cubed. In other words, the physical dimensions of the sports model spacecraft reproduced in the Project Gravitaur documentary seem to favour the standard scientific value of element 115 mass density, not the value endorsed by Bob Lazar. So, what does this mean? Well, it means that the core scientific mystery in the Bob Lazar experience at S4 is the reconciliation between the standard scientific value of element 115 mass density and the claimed value of element 115 mass density. In other words, reconciling the difference between the Frick limit and the Lazar limit. It is also important to note that the same core issue featured in our scaling problem episodes. Well, that's enough from me. Thanks for your time. We hope you enjoyed the video presentation. Please feel free to reach out to me utilising the email address appearing on the first slide.